Alright, so let's continue with this exercise. This part hopefully won't be too long. The part D is probably going to be longer, so I'm probably going to stick with separating this into different parts. So anyways, for each I, the function that sends xi minus ai over epsilon, or this function sends the open interval ai minus epsilon, ai plus epsilon, to the open interval. Well, if you plug in the first one here, you'll get ai minus epsilon minus ai over epsilon on top, which will end up with -1. So this will be -1, and then we'll also get +1, which is the support of f. Again, this is, well, first of all, when I say the support of f, I define that in the previous part. Again, it's just f is 0 outside of the open interval from -1 to 1, and f is positive on the open interval from -1 to 1. But yeah, here's where we're really starting to get into these functions really being a problem. So here, when they say f, it's ambiguous. Do they mean the function f that they define in part A, which is supported on the open interval from -1 to 1, or is it supported on the open interval from 0 to epsilon, which is the function f that's described in part B? And so like there's been some issues in this textbook that I've seen with like trying to like get into these like important facts like this, but maybe trying to dive into these exercises without building the foundation as well as it could be. But again, I do sort of see the merit in trying to get to deep theorems quickly, and so I do sort of understand that. But having this confusing notation with functions is just not really acceptable. It's not something that you should be doing. So you do have to take a little bit of time to sort of like when it says f here, you have to sort of use context clues to see what function they must be referring to, because there's two possible choices, because he used the letter f twice already to mean two different things. And you look at it and you see, oh, well, he means this function which is supported on -1 to 1, because we want g to be positive on the intervals of the form ai minus epsilon, ai plus epsilon. Okay. So anyways, what does this tell us? This tells us that the function f of xi minus ai over epsilon is supported on the desired interval ai minus epsilon, ai plus epsilon. Okay? Thus, g is supported on, let's see here, we'll call this, that this is, sometimes like you might use like capital I to refer to like a a box, meaning that it's like a direct product of intervals might be, you might use the notation capital I for that, I believe. Oh yeah, because you use the notation capital I if it's just a single interval, and so it sort of makes sense to use a similar letter notation if you're referring to a direct product of intervals. So anyways, we'll take this direct product set, we'll call it I. It's an open box in Rn, and so thus G is supported on I. And if you're writing this up as a proof, it might be good to go into a little more detail here. Basically, the reason that G is supported on I is that if if you choose any xi, if any xi is not in the interval ai minus epsilon comma ai plus epsilon, then f applied to xi minus ai over epsilon is going to be 0. And so when you evaluate g at this point, one of the factors is going to be 0, and so the whole thing is going to be 0. Therefore, if any coordinate of therefore for any point in Rn, if one coordinate does not lie in the corresponding interval of I, then g is going to evaluate to 0. And furthermore, if you choose a point in Rn, if you choose a point that is in this set capital I, then for every single coordinate xi, that xi lies between ai minus epsilon, ai plus epsilon, which means that f at xi minus ai over epsilon will give you a positive number, because that's where the function is supported. And so when you look at g, it's going to be a product of numbers, all of which are positive numbers, and so the product will be a positive number. Okay, so by that reasoning, thus g is supported on I, i.e. g is positive on I and 0 elsewhere. So all we need now is to prove that g is C infinity. Since each function xi minus ai over epsilon is C infinity, so is each f xi minus ai over epsilon. Because here we see that this is just a composition of two C infinity functions, and as we've discussed, compositions of C infinity functions are C infinity. And the fact that f is C infinity was proven in part A. Not part B, because part B uses a different function f by the same name, but part A, where this function f is coming from. Okay, so each of these is C infinity. Now consider the function. And by the way, note that like in part A, I had to introduce a function f bar, and in part B, I had to introduce a function f tilde. I used different, even though like I used the same letter, I made sure to put something different there so that I never called two functions the same thing, two different functions the same thing. So now we're going to consider a function, we're going to call it h of x. And x, of course, is in Rn, and so this is really it's h of x1 all the way up to xn, and it's given by the product of x1 times x2 times all the way up to times xn. Since if you take the ith derivative of h of x, what's going to happen? All of these, you have x1 through xn in this product, but when you take the derivative, every single one of those will be considered a constant except for the xi, which when you take the derivative will drop out. So what you're going to end up with is x1 times such and such, and then you'll get up to xi minus 1, and then the xi term will not be included because you take the derivative, and so you'll skip it and go up to xi plus 1 and then continue all the way to xn. And of course, this is assuming that I is strictly greater than 1 and strictly less than n. If I equals 1, then you would just go x2 times x3 times all the way up to xn. And if I is equal to n, then you would have x1 times x2 times all the way up to times xn minus 1. So anyways, so dihx equals this. We can see that all partial derivatives of h of all orders exist and are continuous. And how are we able to see that? Well, what happens is that every time you take the derivative of h with respect to a particular index, if you take the derivative of h with respect to, say, I, then if xi, the term is still in there, and you pull it out. So let's say we have this dih here. If we were to take the derivative with respect to j of dih, then we would just find wherever xj is and pull that out of this product as well. Now, if j, in the case of j being equal to I, then since the function dih does not depend on the variable xi, which is equal to the variable xj in the case of j equals I, then taking the second derivative will give you just 0 because you'll be taking the derivative of a constant. And we also see that every time we take so basically every time you take a partial derivative of h, you either remove one of the xi's or the whole thing becomes 0. One of those two things will happen, and in either case you'll be left with a continuous function. Therefore, partial derivatives of h of all orders exist. Eventually, if you take enough partial derivatives, you'll get 0, because if you take d1 of d2 of d3 of blah 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 of dn of h, you'll just be left with 1, because you'll have canceled out every single xi term. And then if you take the partial derivative of the function which is constantly 1 with respect to any variable, you'll just get left with 0. And so eventually you'll get down to 0, and 0 is c infinity. So the whole thing is c infinity. But of course c infinity here, because this is a function whose domain is Rn, you need to be concerned with the partial derivatives. Okay, well actually, on that, so partial derivatives of h of all orders exist and are contiguous, thus the nth total derivative of the nth order total derivative of h exists. Wait. So here's what I'm going to write now. I'm going to write theorem 2-8 may be necessary. Because what's happened here, well, here. So by theorem 2.8, maybe we conclude that h is c infinity. Because what's happening here is that when you think about differentiability or continuous differentiability of functions of several variables, what you really do is you really only have to look at the partial derivatives individually. And once you know that once you know that you can take the partial derivatives with respect to all variables and end up with continuous functions, then that tells you that you can take the total derivative and end up with a continuous function. And that's really important, and that's really what at least for me, that's what I like to use when I think about differentiability of functions of several variables. And I think that's been one of my main frustrations with this textbook, is that it doesn't get to that soon enough. There's all these questions that we've been doing about differentiability of functions of several variables, and I want to just look at the partial derivatives, because that's all that really matters. But this textbook really wants you to be familiar with using the limit definition of the derivative instead of just throwing a theorem like theorem 2.8 at it. And I do understand that, and it does give you a deeper understanding of the material if you're able to use different types of tools to attack these problems. I think that using partial derivatives is just the easiest and most natural way to approach these types of problems, and so I would have liked to have seen this result earlier on before having to do all these exercises, so that I could just apply it straight away. But here we are. However you want to do it, you can prove that h is C infinity. I think you can also do this by using induction by one of the theorems in this section or the previous section that looked at the differentiability of the function p of xy equals x times y. And you prove that this function has total derivative given by whatever, and you can use induction on that to prove that any function of the form h will be C infinity. So anyways, conclude that h is C infinity. Since g of x, it's what it really is we're taking h of f of xi minus ai over epsilon, comma, dot, 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 comma, fxn minus an over epsilon. So g can be written in this form because all we're doing is we're taking these fxi minus ai over epsilon. Okay, this should be 1. Because you go from x1 minus a1 over epsilon all the way up to xn minus an over epsilon, going from integers from 1 to n. So you just take these things and you multiply them together. So what you're really doing is you can think of these f's as being different coordinates and being fed into the function h. So this, which is a composition of C infinity functions, I should use another line, functions g is a C infinity function. Alright, and that's all we need to prove. I guess one other thing that we might need to do here, if you want to be super pedantic, is that technically it's not entirely clear that, like, when you prove the composition of C infinity functions being C infinity, what you're really using is the chain rule. And the way that you're using the chain rule here isn't entirely clear, because on the left-hand side we have g of x, and on the right-hand side, well, each argument of h involves just one coordinate of the vector x. And so it might be unclear how this is actually in a form that allows you to apply the chain rule, because you need the same variable on both sides of the equation, obviously. Well, what you can do if you really want to be pedantic about it is you can, instead of writing x1, you can write pi 1 of x minus a, and then go all the way up to pi n of x, where pi I is the projection of, it's the projection onto the ith coordinate. So if you plug in an n-dimensional vector, then pi I will return the ith coordinate of that vector. And this is something that we've discussed in the chapter already, and we've proven that these projection functions are continuous. And have we proven that they're C infinity? They are, but I'm not sure if we've proven that. I mean, basically what you do is, for the projection function, if you take the derivative with respect to, for the projection function pi I, if you take the derivative with respect to j, where j is not equal to I, then you're going to get 0 because it doesn't depend on a j. But if you take the derivative with respect to I, then you'll just get whatever the partial derivative of the original function is with respect to I. And so from there, right, so when you take the derivative, you'll just end up with, so whatever's in here, you can basically use that reasoning to prove that these projection formulas are continuous and they do everything that you want them to do. But yeah, so G is you've really got like a whole bunch of compositions of functions going on in here. But it's all fine. All of these functions are nice functions. They're all C infinity. Take compositions of C infinity functions. You get C infinity functions. It's all fine. Don't worry. And yeah, once you have that, you get that G is C infinity. And we proved that it's supported on the set I already. And so this finishes this part of the proof.